either a detached troop with respect to things going on during their surveillance mission, or with respect to mixed air combat teams and beyond visual range air combat, some terrific simulations. So my expectation was that we'd be spending most of our time looking at this fun component here, which we've been calling design, and that, yeah, there'd be some work in Orient as well, because after all, the data needs to be interpreted in some way, shape, or form. And we couldn't have been further from the truth. It was more like this. We're doing a lot of work in situation awareness, and as I'll get into, some work on decision making. And of course, our roboticists kept saying no. In fact, most of the work's down here, of course, with respect to the sensors and the effectors. And so everybody who was looking at this from a different perspective had different ideas as to where they were going to be focusing on. In addition to the agent control applications, which I described a moment ago, not only ours but others, I'm happy to say that there's a widening range of such applications, not just with respect to mobile robots and a lot of game theory and so on and so forth, but also with respect to decision aids. There's a terrific application on cyber defense decision aid that SIFT and others have put together over the last couple of years that uses a goal reasoning approach. And Alexei has described, amongst other people, its use for narrative generation. There's also an outstanding example of using goal reasoning for, of all things, cooking, in particular design, recipe design. So here's a picture of Julie over here, and the idea being that what Kashan Grace and Mary Lou Maher are interested in is being able to learn environment models, using deep learning techniques, by the way, and in doing so, apply those environment models to push the direction of search towards goals or in the environment, and the goal being to explore curious locations in the environment that have both value as well as novelty. And it's very interesting. Okay, so let me give you a status update as a core part of the survey, so to speak, as to where the community is with respect to the approaches that they've been looking at. So we've got some foundations on it so far, I'm happy to say, in terms of some early models that we've been looking at, as well as some very theoretical models for explaining to others what we're doing. I'll also describe some of the individual components that we saw before in some detail and user interaction. So our earliest model is one that we were calling goal-driven autonomy, and it's the very obvious thing that perhaps you've seen time and time again. It's one that starts with notable event detection. Something's going on. Then the question becomes, can we learn something about it? Can we perform diagnosis to explain what caused it, so we can use that information for purposes of determining how to respond? Oftentimes, the response would be to select a new goal to pursue, and then there are questions of goal management, which we haven't done a good job of really exploring. We developed an agent called R2 that pursues this, and in an initial study, as shown here, we were able to identify that, in fact, all of its steps were crucial for its performance, which was helpful to us. And that was the style of some of the research we were doing early on, this with respect to the simple Navy task. We've since taken that model, goal-driven autonomy, or GDA, and extended it in a variety of ways by maturing the way in which it's doing notable event detection, explanation, generation, or goal selection. And I'll touch on some of these as I go through. In terms of the theoretical foundations, the best work has come out of Michael Cox, perhaps, in terms of his work on learning and goal reasoning. And you can find that in 2015, in which he defines a set of functions for goal change, goal transformation, and learning and anticipation. Well, we've done some work ourselves, and I'd like to present that to you in a couple next slides, which we've been calling goal refinement. There's also been a lot of work on the individual components of the loop as well, such as that for explanation, generation, iterative, explanatory diagnosis, as well in the decide category, such as goal distribution, sensitive planning that Daniel Barajo has just presented at the workshop last week. But I'll focus on goal refinement first. So, goal refinement is an extension of what Rauch and Papadi's group is called plan refinement. This was introduced quite a long time ago, and it frames goal reasoning is a process of iteratively adding constraints. And it looks like this, in which there are two things to highlight. There are a set of modes that capture each goal and its set of constraints. And there's also a set of strategies that allow you to move from one mode to the next. starting here at the formulation strategy. And what happens is that you're processing, by adding constraints to goals, the goal throughout this life cycle. And also you have the opportunity, if need be, to be able to resolve certain strategies because certain situations have arisen that require additional attention. In this case, for example, you could not only just simply repair an existing plan, but re-expand it in a different way, or defer it, or indeed formulate a new goal to address the problems that you're addressing. You can relate goal reasoning to replanning by using this goal life cycle. Replanning is distinguished in the sense that it doesn't support some of those formulation and earlier capabilities, nor does it support all the resolve strategies that we saw just a moment ago. Likewise, we can use this goal life cycle to situate the goal-driven autonomy model, which doesn't have all the resolve strategies itself, it just has one. Whenever something goes wrong, forget the plan, just reformulate the goal and away you go. We've also used it to relate some of our own research that focuses on a specific strategy, as in the case of these three things here, or down here we've developed an implementation of the goal life cycle that we're using and making available for everyone, called ActorSim, that I'll describe in a bit. Okay, so some of these exist. I'm happy to see that they exist, and I can give pointers to them. But the real guts of what's been taking place in this area has to do with the actor processing components. So I'll start with observe, and I'll cycle through. So there's been some work on emotion influence perception, I'm happy to say. Alexandra Coleman has been responsible for this, in which she's pointed out that moods and perception are interdependent with each other, and she's bringing this to the goal reasoning perspective. There's been recent work that has been described in which, by Michael Cox and his student, on rationale-based monitoring, in which the idea is that you are planning by making sure that there are certain things that you're sensing in the environment that are critical during the vision, such that if sensed would generate replanning episodes. We've instead been looking at using deep learning techniques directly for goal selection, and I'll demonstrate. So we've been influenced by some of the work that's going on with respect to AlphaGo. We're not up to the point using deep RL yet, but we are in the point of using similar techniques for navigation, and in particular focusing on the task of sub-goal selection. So we've been doing this with respect to Minecraft, which is becoming increasingly popular, and we've embedded this with the ActorSim system, which I'll describe in more detail later, where the inputs are the goal location, current or previous locations, visual cues in pixels, visual information in pixels, etc. And it's just a small subset of sub-goals for what our agent is going to be doing as it navigates from a start location to a goal location in that environment, as somewhat depicted here from the gold to the green. And what we've been doing is training this conversational neural network to select the correct sub-goal. Started with AlexNet, and we found that with a comparatively small number of iterations, comparatively short period of time, that it was outperforming the baseline of 25% quite quickly. And we knew why it was making errors as well, because we was using a memory-based approach. We moved to a memory-based approach. We think that we're going to get more out of these kinds of algorithms. So we've got our hands wet in that to some degree. On to Orient, where a lot of the work really has taken place. Here, the first topic is that of notable event detection. So, as mentioned, one of the first steps you have is to be able to identify that something has occurred in which you want your agent to be focused on. A lot of people have looked at this and said, well, we can pre-encode expectation models of all sorts in order to be able to highlight the fact that something has occurred in this regard. Dannenhauer, Dustin, working with Hector Munoz Avila and others, has looked at using domain ontologies for this. The folks at SIFT and those working with them have looked at encoding models for identifying network attacks that take place. We've, in looking at a continuous space, been bounding expectations to greatly reduce the false positives that occur when you're looking at notable events or trying to identify them. We've also looked at using natural language grammars and domain-specific models for the kinds of tasks that we've been looking at. But a lot of others have looked at learning the expectation models directly, such as Mike's work with others on, Mike Cox that is, on learning distributions and state predicates and comparing them using a distance. Or learning joint distributions of design parameters, which is what Catherine Grace and Mary Lou Maher are doing with respect to the design domain, which I described earlier. Or learning goal distributions for purposes of trying to anticipate what goals will take place so you can prepare for them in an environment in which real-time response is crucial, and that's what Daniel Barajas' group is doing. There are others, such as Michael Targ and his advisor, who are instead saying we really want to combine different types of expectations, where he's got models of naive physics, different types of simulations, geometric reasoning, etc. And what he does is he uses what he refers to as a normality tree diagnosis approach to combine this. It's a data fusion test of sorts. The second step is that after detecting these types of events, the question is what methods have been used so far for purposes of trying to explain their causes? Michael Cox, again, has resorted to something he's very familiar with, which is explanation patterns to do this, in which he's pre-encoded patterns, cases, if you will, and in particular different types of episodic encoded patterns in order to be able to explain why a particular event occurred. In contrast, we and some others have been using abduction dynamically in order to be able to adduce events or actions from the event histories themselves. We've formalized models of surprise and for plausible explanations of doing this. We've even gone so far as to being able to say, once we formulate these models, that why don't we learn them and generalize from them, and then apply them in the future. In contrast, Robert Golden and others have used a Bayes net sensory fusion approach of observations in order to be able to generate rules that look like that given certain sensory reports, network intrusions will automatically generate certain events. There's also a strong interest in this area in terms of plan and goal recognition. We've done some work on ourselves. The idea being that oftentimes after you have abduced or otherwise identified certain events that have taken place, and explained to some degree, that can be passed off to these algorithms here in order for them to have more information to go on in order to be able to do more accurate plan and goal recognition. And in fact, it's symbiotic. Once they work, they can pass off their information back to the other algorithms in order to be able to further diagnose what's going on. So we worked on a case-based noise-tolerant plan recognizer that uses a type of novel representation. Others have looked at a variety of different types of plan recognizers, oftentimes for generating expectations of some type or another. A little bit different from that is the work that was just described at the Go Reasoning Workshop, which was by Gal Kamik and his students, in which they're not looking at a library-based plan recognizer. Instead, it's one that uses a planner to generate the recognition hypotheses. So I've gone over observe and orient, and there's some interesting work in design as well, which begs the question, how should you react in the first place? So, of course, one thing you might want to do is that once you've decided that you understand what's going on, you might just ignore it, and so that's been highlighted. But in general, most people are talking about as formulating or selecting a goal. So this might be done by interacting with the user in a very straightforward way, which is what we were doing with our work on active learning a few years ago. Or others might be using a simulator or otherwise to select a learning or information gathering goal, which is what some of Mike Cox's work has been on. But the majority of people have been working on automated approaches for selecting a task performance goal, and I'll list some of them in just a moment. I've already described some work by Grace and Maher on pursuing creative design for solutions, which is very interesting and quite different style from the others. So for goal generation, this comes from our earlier survey. Most of the work has fallen into reaction to problems that have been observed as opposed to affordances that have been recognized or opportunities that have been recognized. Oftentimes, those problems could be either split into the categories of being externally or internally motivated. So, for example, subgoaling goes back to for ages and has been looked at in these models. Mike Cox has looked at ways of just simply negating a model's antecedent. There's been work on matching relevant conditions of long-term goals in the context of Icarus. There's been work by others to be able to extract cases from learned expert game traces. The idea being that if you have traces that have been captured and you can see where, and you can compare your state with previously captured states from expert game traces, you can use information pertaining to where you want to be in the future based upon those experts' decisions and modify your goals accordingly. There's been some work in character reasoning that Alexei has looked at, as well as some real interesting work on goal transformation that Mike Cox has looked at with others again. There's been some work on internally motivated approaches, some of which is our own. So for example, we've looked at domain-independent approaches, getting away from some of our earlier domain-specific approaches. Alexander Coleman, who's just joined us, is very interested in rebel agents, which are those agents that have access to information that you, the operator, may not have. And so the agent may come back to you and say, no, I'm not going to do what you want me to do because I know better, and I'm going to give you some other recommendations, and let's talk about it. And then we've also looked at a variety of other approaches. So affordances differ because in this case you have that opportunity, you can pursue a better goal because because the agent was considering it but couldn't pursue it before, but now you can. So in that case, what Garnier and others have looked at is learning behaviors related to affordances of interest, whereas in contrast, others such as Schemmerhorn and those who he's working with were looking at using counterfactual reasoning approaches for doing the same. There's been a lot of work on goal prioritization, meaning that, and we separate this out from goal selection because we're maintaining a set of goals over time. The way that people have looked at this is first check to see whether or not the goal has already been achieved, which has been an interesting thing. Once generated, you think would be novel, it's not always. A lot of people have used this basic idea of associating associating intensities with the goal generation procedures. And those intensities may have some sort of numeric value in a very straightforward way. And there have been other fairly straightforward ways that use numeric estimates of the utility of a particular goal. More important perhaps for us has been the work on plan execution cost estimation, meaning that you need to get feedback from the planner itself as to how good a plan is for a particular goal that you've chosen, because you can't come up with a good plan for a very important goal. You might want to abandon the use of that goal in the first place. So there are a few folks who are beginning to look at that now. There's been some bias towards collaborative and team goals versus individual goals, and that's been described in the workshop. And there's some really interesting work that Nick Hawes and his students have been doing over the years in terms of learning goal priorities. They learn what are called goal priority profiles using a case-injected genetic algorithm, and they apply these to dynamically guide high-level strategies. And the result is that they found that it outperforms a static goal profile. So I've been running through these fairly quickly, and let me get to ACT. This is where I put the work on planning. There's been some work on some some lower level planners, reactive planners, and some of the others that I described here. Although I must admit, Daniel's one is very interesting because it's got this, because of his use of soft goals and state-dependent cost functions. But most of the work has been with respect to hierarchical planning algorithms and networks, such as hierarchical task networks, which are one of the older varieties. This has been looked at both with respect to using the basic algorithms as well as those that use nonlinear continuous, that are trained to handle nonlinear continuous effects and modify their ones. And there have been other modifications to the very popular SHOP2 HTN algorithm for handling in a proactive way monitoring tasks for computer vision, so as to ensure attention to specific types of notable events. But more recently, there's been some work with taking HTNs and swapping out the task semantics for goal semantics. And in doing so, that brings it more into line with the needs of the goal reasoning researchers who are working on these things. There's been some work, for example, on qualitative models and goal hierarchies by Ken Forbes and Tom Hendricks, as well as some work on variants of TMK language, which is itself a variant of HTNs, now laden with goal semantics. But I'll mention very briefly some of the work that our group has done with respect to what are called hierarchical goal networks and goal task networks in the next few slides. So, in the context of the goal lifecycle, which I described earlier, there's a point in which you're generating plans. Automated planning is a very important part within this context of goal reasoning. You'd like to be able to use these hierarchical planning algorithms, but they require substantial background knowledge. You need an admissible heuristic in order to make sure that they work efficiently and effectively. And they weren't available for hierarchical algorithms previously. So what Vikas Shivashankar did working with us is to take an admissible heuristic from classical planning, put it into his optimal HGN planner, and showed that it outperforms an optimal classical planner, and in terms of the number of problems solved, in terms of the tasks that two tasks he was looking at, as well as reducing the number of nodes expanded. My ex-postdoc, Ron Alford, took this a bit further. He said, look, it's nice to be able to work with goal semantics, but we really need both tasks and both semantics for both tasks and goals, and no existing formalism supports them. So he invented such a formalism called goal task networks, provides a unified semantic foundation for planning that we're able to use and perform a first complexity analysis, and showing that they're the same class as our HTNs and HGNs and the algorithms that operate on them. And we're taking it a step further. Ron described this just this past week. Okay, so a couple of notes in regards to the memories that people have used and models that people have been looking at. There have been a lot of them. We've talked about this notion of a goal network and used it many times with respect to some of the robotics tests in particular that we've worked on. And I mentioned to you earlier the goal matrix view on this. What Hector and his previous student, Ulla GD, did was they introduced and learned a mapping from goal discrepancy pairs, as they call them, to a set of different goals associated with certain values that they update over time using a reinforcement learning algorithm for purposes of informing as to what goal you should switch to when a certain discrepancy takes place. Alexandra Coleman has instead been looking at autobiographical memories, and Hector has been looking at issues of what goals were achieved and outcomes obtained in order to be able to increase the capabilities of the algorithms that they've been working with. There's been a lot of folks who instead have been looking at learning these models over time, using a variety of different types of approaches. For example, we've looked at case-based and adaptive learning approaches in this regard. Mike and his group have looked at different types of tree induction approaches for learning goal formulation knowledge. And Cooter and others have looked at learning goal hierarchies directly from the data, using, and this has been addressed using a variety of different techniques by others. Very few people have looked at learning affordance behaviors, to my knowledge, at least in this context, but Olivier Georgion and his students have done so. We've instead been looking at learning exogenous event models using Discover History, an algorithm that Matt Mono developed. And there are others who have been looking at predicting future learning goals, as well as expectation models, the type that Grace and Mono have been looking at.